I think we are in air. I'm not completely sure if you are in air because I can't see the slide yet, but if we are on air, good morning, everybody. I'm not sure if you're on air. And at the same time, I hear myself in the background, so it's a bit it's kind of exciting. So let's see if we probably can change this. To be honest, I don't see myself. So we can change this somehow, and if you can stop the echo, it would be perfect. Okay, can you hear me now? But now I have the problem to hear the background noise. Is this okay now? And I can't see the slides. So sorry for this. I just have to talk to my friends in Milano if they can make it work. Do you hear me now? Perfect. Thank you. Thank you, Umberto. Okay, and can you see the slides, Umberto? Talk to me. No, not yours. Mine. It would be great if I could see them myself, but for some reason I can't. Okay, here we go. So sorry for this start, and it will become better with time. So when we talked it as to take the decision to go for a virtual meeting, which was in March, we had facing the problem that we thought, well, probably it's too early to decide in December, but the situation is that it obviously looks like we did the right decision. So we had a virtual meeting, and it looks like, besides some technical problems in the beginning, which is actually related to my own limitations in techniques. If I can get the next slide, please. You will see that we have a nice number of abstracts available. It's more than 1,000 participants. It's more than 1,000 abstracts. Of course, we lost some in relation to the proto meeting, which we would have. More than 500 orals, 400 posters. And the number of sessions is about what we were expecting to have in Porto. So it's 73 sessions we were expecting, and this is what we have. And next slide, please. So I want to take the turns. We still have a couple of minutes. I'm sitting here in my living room. It's at the same time my home office. It's my kitchen is everything. We still have 50 minutes before the plenary starts. I want to take the possibility to talk a bit about the EAP, the development, and the future of EAP. And I want to take the chance to talk first about the animal family. The animal family, which is, as you know, is the flagship of EAP. The next slide, please. And it is done in a consortium together with INRA and the British Society of Animal Science. The management board is led by the chair, and it is Nigel Scolan. I don't know if you hear me now from Ireland. Thanks a lot for your fantastic work you have done over the last decade, you can say. And he will be replaced in January by Jaap van Lieken. He's from the Netherlands. He's working for INRA. It will be a very smooth transition because Jaap is very experienced. He was on the management board for quite long, so we're quite sure that we will do a fantastic job. The next slide, please. Animal, as you know, is the International Journal of Animal Bioscience, which we published, and we now add the Animal Science Proceedings, formerly called Advances in Animal Bioscience. Next, please. And the Animal Consortium fully supports the open science agenda. Therefore, we have taken the decision to move the journal to become a gold open access. It will be published now by Elsevier, so we had to change the publisher. We're starting in January 2021. So all authors which have submitted papers after June 2020, their papers will be published golden access. The rate, the fee is, I think, relatively moderate. It's 1,400 euro. And related to the quality of the journal, I think this is more than fair. Next slide, please. Animal is, as I think, one of the best journals in the area of animal science and vet science. And this is thanks to many people working on it, mainly, of course, the editor-in-chief, which is Isabel Ortiz. If we would have met in Porto, I would have asked her now to stand up in the audience, which is not possible. Isabel, thanks from here for all your work. Not doing alone, you have section editors, you have reviewers, and of course, most important is the authors, which are assuring a certain quality and high quality of the papers which are submitted. So next slide, please. So over the years, we have developed a nice impact factor, is 2.4 now. So we are ranked number 9 out of 63 papers in the field of agriculture, dairy, and animal science, and number 11 out of 142 in the area of veterinarian science. I want to dedicate a word to the young people, which hopefully are listening to us now. Impact factor is important, but impact factor is, of course, not everything. So the quality of a journal is not only related to the impact factor, it's especially related to the quality in the review process, which is important. Reviewing is the only possibility to assure the quality of science and the high reputation. And what we see during the pandemic situation is that we still have a high number of people which are believing in science. And this is all about reputation. So if there are some journals out there promising you a review process of days or weeks, it can never be serious. And I want to ask the young people not going for the fast success, taking the procedure of a review, and it will always improve your paper. And what you have published is there forever until your grandmother, your grandfather, and you want to be sure that to your grandkids you can show papers you have published with a certain quality. Next, please. The second one is Animal Science Proceedings. The editor-in-chief is Glad Thomas. Hi, Glad. I hope you have internet connection down there in Italy. This is about the publication of high-quality conference, symposium, workshop proceedings. So if you have something in line and you think that this has a value to share with the rest of the scientific world, come in contact with us and we hopefully make it possible to publish it in Animal Science Proceedings. Just contact Glad Thomas, the editor-in-chief. Next, please. So if you look for more information, just visit the homepage of Animal or of Elsevier and you get some background information. And this brings me to the point, next slide please, that do not be confused between singular and plural. There is Animal, which is the original, and there is a plural version, which we of course don't like, not because we are shy about competition. We don't like that some people using the reputation of names of journals by just giving a plural and then confusing authors and reviewers. So be careful when you submit your paper. You want to be in the original, not in the fake journal. Next, please. So unfortunately, we cannot have, we will give away the awards, but we don't have the procedure. And this is actually a shame that we don't have the procedure. But nevertheless, of course, we want to give a special attention, next slide please, to the people. And first of all, the one who received this year the most important scientific award, which you are giving away, the Laura Award, is a colleague from Padua, Italy, Giovanni Pitanta. He's an animal geneticist, very well known in Italy, very well known outside Italy, in Europe, and even outside Europe. An extraordinary scientist, and we thought that it is worth to have his talk in front of the audience. So he will give his talk in Davos next year in Switzerland. He will be awarded there. Congratulations, Giovanni. We're looking forward to see you there. The next awards, and the next slides, please, the Distinguished Service Awards. And this year they are going to 3 very well-known people. First of all, it's Maria Klopic, which many of you know. She was president of the Cattle Commission for long. And she was deeply involved in the organization of a wonderful EAP meeting in Bled. Maria, congratulations. Also to Maria Spea from Croatia. She was deeply involved in the Dubrovnik, in organizing the Dubrovnik meeting, an unforgettable meeting. I'm sure if you have been there, it's still in your mind. And Mike Steele, last not least, he has done many services to EAP and animal science in general, organizing, co-organizing the Belfast meeting, being active in many different levels. Congratulations to you. On the next slide, you will see the winner of the Young Scientist Award. And this year it goes to Switzerland. It's Josef Gross. Congratulations, Josef. You will be awarded next year in Davos. It's just around the corner, so it's not a long drive from your home place. Looking forward. Congratulations. It was very competitive. We had excellent applicants, and we're really happy that you are the winner of this award. The next slide, please. I want to talk about the upcoming meetings. On the next slide, you will see the EAP homepage. It's brand new and is also brand blue, as you can see. In the right corner there, you see the homepage. Just go there. And next slide, then if you look deeper, you will see on the next slide, you will see where the joint meetings is exactly. And the next slide are showing you exactly where they are. And as you can see, we have the next meeting in Davos. And there we will drink our espresso from these, I don't know if you see this, from these type of coffee cups. And from Davos, we will then go to Porto. So we decided to have the Porto meeting in 22 in Porto, so 2 years later than original. And they assured us that they will store the food. And I guess even the port wine will be better in 2 years from now. In Lyon, we will be in 23, and then we will go to Florence in 24, a very beautiful city in the middle of Italy. I'm really looking forward to this meeting. Next slide, please. Just to make you a bit hungry for the next meetings, real meetings, I have received some slides from the colleagues from Switzerland, which are Beat Babst and Lucas Casanova and Andreas Hofer. They have prepared the slides and they are ready to welcome you. And I can tell you, Swiss people say they are ready to welcome you. They're really ready. Everything which is needed is well prepared. It is a beautiful place in the mountains in Switzerland. They will certainly take care for your health depending on the COVID situation. They will also take care for financial risk. So please, the next slide. So don't worry, register. You can register early. The homepage is down here. So the registration will start by the end of the year, beginning of next year. Don't worry, in case it will be cancelled, you will be reimbursed. You will be reimbursed in Swiss francs, so you will only win. So next slide, please. Davos is the perfect spot for an annual meeting for different reasons. Now, sorry for the Swiss colleagues, I have added some additional slides. Next slide, please. Davos is very well known for the healing power of the air up there in the altitude. So by tradition, many people went there for lung problems and to become better. And next slide, please. You see one of the famous guests of Davos, which is Thomas Mann, the Nobel Prize winner. He has written a beautiful novel. It's called The Magic Mountain. And as you can see, it plays in Davos, and it plays at a spot where we have the social dinner during the meeting Davos. I tell you, you have to see this. You have to be there. It's unforgettable. So please register for Davos. Davos is easy to reach. We have airports nearby. We have Zurich nearby, Munich, Innsbruck. You can fly in and take a train, and you reach it very, very comfortable and easy. Next slide, please. So we have a little video prepared, and I want to ask Milano to play this little video showing a bit about Davos, please.
For years, it has been certain that the 72nd Annual EAP Congress 2021 will take place in Davos. If we had had to choose a corona-suitable location at that time, our choice would have been Davos. Davos is a small place with lots of space and good air, which is why people with asthma and other lung diseases still travel to Davos today. The well-structured location allows for effective application of protection concepts. For years, Davos has been used to operating safely in special situations, such as the World Economic Forum. And Davos has a perfect Congress infrastructure. Therefore, dear EAP visitors, register from the beginning of the registration process. We make it possible for you to avoid any health or financial risks. We will have a comprehensive protection concept ready for the Congress, and if you are unable to travel to Davos due to Corona, we will automatically switch your registration to virtual participation and reimburse the difference in registration costs.
Use this almost unique opportunity to meet professional colleagues from all over the world. This is better possible in Davos than in many other places. Even if Corona should still rule the world in 2021. We are looking forward to meet you in Davos.
Thank you very much. So I hope that you have heard and had some sound. I didn't have, but I heard it before. And I can only invite you to go to Davos. It will be an unforgettable event. Now, if we can go back to my slides, please. I have still a couple of these slides to show and share with you. Just takes a bit and then you're there. While you can enjoy my living room while colleagues from Milano are looking to find the slides. Can we go back to the slides, please? No, Umberto, it's not your turn yet. Still my slides, I'm not finished. It looks like we have some problems with the slides. It's not a problem for me. Don't worry. I probably have them in mind, what I wanted to show and share with you. So I do it without slides, Elisa, don't worry, I will do it without slides. For me, actually, and this is, I will take the last 2 minutes, no problem. The last 2 minutes to use them to say goodbye and thank you. It is my last term as a president. I can't say that this type of tactic is the highlight of my time during the EAP, but it works and will become better over the next year, I'm quite sure. I want to say thank you to a couple of people, the representatives of the different countries, the trust they gave to me, giving me the pleasure and the time to stay on board for more than 4 years. But of course, I want to thank the closest staff and people supporting me. This is mainly the council. And the council members I had on board, I was more than lucky because they were excellent, very supportive, really friends, still stimulating and challenging, asking the right questions and at the right time. I had a perfect support. Sorry that I'm not mentioning all your names. I have most of them in time, but there's a risk in my age that I'm missing 1 or 2, and this I don't want to do. Thanks a lot to the council. I'm quite sure that you will continue your work, those which are not leaving with me, and please stay active as you was. Secondly, I want to thank, of course, the office in Rome, which is like a family. It was like a family. It was fantastic always to go to Rome. It was a pleasure to work with all of you. And I know better than everyone that you go far behind most of the time that we can expect from a normal employee, especially around the conferences, but also in normal times. Thank you very much. So fantastic to be with you. I want also to announce that one of the core members of the office in Rome, she gave birth to a baby, Eleonora. From here, I'm not sure if you can listen and follow the meeting in your hospital room, but if so, congratulations from all of us to your boy. Milo is his name. Stay healthy. And some may say, how can she give birth during the meeting? This was, of course, not planned. We had planned to have the podium, so everything was done right and perfect. The last announcement, and then it's time to move on to the plenary session. The last announcement I have to make is that after I'm leaving, it will be going even better for EEP because we have chosen a new president, which is certainly a fantastic choice. For the first time, we have a woman on board. It's more than time. It's Isabel Casasus from Spain. Isabel, I'm really happy that you take over, and I'm really sure that you're doing a perfect spot. So whenever you need help, we are around, Isabel. So thanks a lot for your attention. Sorry for the technical problems. You can believe this was even worse for me than for you. And I think we can move on directly to the plenary session. We don't have the slides yet, so hopefully you have the program in front of you. We're talking about climate change and the impact on livestock, and I think that we have 3 excellent speakers on board, and I see that they're all already waiting in the waiting room. I can see this on my screen. We want to start with Georg Karse. You know, there is a lot of talk about there's a lot of talk about the models we are using to estimate and predict the climate change scenario we are expecting. And we have someone, the third speaker, who will give us a talk about, with the title, 1.5 degree global climate and climate politics. And Georg Karse is probably the best speaker we could have for this topic. He's Italian by native, but he's working in Austria at the Institute of Atmospheric and Cryospheric Science in Innsbruck. His research interests are mass and energy balance on glaciers, fluctuations on climate and glaciers, and international and national levels, freshwater availability and demand, global glacier mass change and drivers. He is currently Dean of the Faculty of Geo and Atmospheric Science. He is full professor for climate and cryospheric research. He was very much contributing and also lead author of several IPCC reports, assessment reports, and technical papers. So he's very deeply involved, and this is also why he was part of winning the Nobel Peace Prize in 2007, which was dedicated to Al Gore and the IPCC team, and he was on board. Since 2017, he is full member of the Austrian Academy of Science. Georg, I know that you're extremely busy. You're giving talks all over the world, and we're more than happy to have you on board. And now I ask you to go on stage. The floor is yours.
Thank you, Matthias. Ladies and gentlemen, dear colleagues, I am just trying to solve the technical points now. And I very much hope that you can see my slides now. Okay. Good morning to you. I'm happy to having been given the opportunity to talk to you about global climate, climate policy, and it is concentrated around a number which is the plus 1.5 degrees. What does it mean? This goes back to 2015. Okay, can I go to the next slide myself, or does anybody have to do it? I obviously can't. Is it okay for you if I stay in this mode? Somebody has to talk to me, not just write a comment, because I can't see the comments if I stay in this mode. Can anybody tell me whether this is okay? Obviously, I'm not able to go to the next slide. Anybody help me? Regia. Yeah, that's fine for me. Is it? Yeah, yeah. Yes, that's what I do already since 1.5 minutes, but it doesn't work. And the Regia tells me that I have to speak without slides. Yeah, shy. I mean, it's a different story then. Totally or with this F5 option. Matthias, can you hear me now and can you see the slide? Okay, so I proceed with this one. It is this 1.5 degrees Celsius that I'm starting with, and this comes from the 2015 Conference of Parties, the 21st Conference of Parties of the UN Framework Convention of Climate Change. It's composed of 196 national governments, and they have achieved this agreement, this Paris Agreement then, which is also illustrated in this figure here. And it says that all the governments are aiming to hold the increase in the global average temperature to well below 2 centigrades above pre-industrial levels, and to pursue effort to limit the temperature increase to 1.5 centigrades above pre-industrial levels, recognizing that this would significantly reduce the risk and impacts of climate change. Article 2.1a of the Paris Agreement, and you see the illustration below. Now, at the same time, the Paris Agreement, or the UNFCCC, asked the Intergovernmental Panel on Climate Change, so to say the scientific part of the whole process, to prepare a 1.5 degree special report, since this was a new number coming into discussion. This report was delivered in October 2018 in an extremely short time. And it did not just show that these targets are feasible, it also showed that there are differences, whether we go for 1.5 or 2 degrees Celsius. And more than anything else, they did show us how we could bend our current warming rate, and current means by 2017, how we could bend that into a way to stay within these green shaded areas, which reflect Article 2.1 of the Paris Agreement. And the pathway to follow is that the CO2 emissions need to meet a net zero level by 2050. And there is an intermediate target to be met and to be gone for, which means minus 45% from the 2010 emissions by 2030, which is in about 9 years from now. Now, time has passed since then, and we have gone, with temperatures, we have gone up a little bit quicker than the 2017 current warming rate. We have already reached 1.1 degrees above pre-industrial, and there was just 2 or 3 weeks ago probability estimate published by the World Meteorological Organization, and they say there is a 20% chance that already within the next 5 years we would have the first year with a global mean air temperature of 1.5 degrees. So we are much, much faster underway than we thought a couple of years ago. But what does it mean? A temperature, half a degree up or down is not very much, and we would hardly change a jacket or put off or on a jacket if we change a room temperature by half a degree. But the temperature stands for the energetic state of a body or a system, and the average temperature of the Earth's surface is the expression of the energetic state of our climate. And this is also expressed in this famous Stefan Boltzmann equation, which relates the energy emission from a body, which of course has to come from somewhere, so it also stands for the energetic state of this body, to the fourth power of the surface temperature. So you can imagine that there are big numbers behind in terms of energy, and if we observe a change in this surface temperature, then we can assume or even calculate a change in the energetic state. The reason for the changes, the present day changes in our surface temperature, is the emission of fossil fuel carbon. And this is the main driver. We have also other greenhouse gases. And we are about to emit 10 pectagram carbon per year, which is the same as 10 gigatons per year, a little bit less. And this is equal to the total amount of the excavation mass of the Brenner base tunnel 200 times per year. So that's what we are emitting, and the respective energy income through the physics of the greenhouse gas processes is approximately 250,000 times the energy which was delivered by the explosion of the Tsar bomb, which was the biggest bomb ever having been exploded in 1961. And so far we have accumulated the amount of energy equal to about 10 million of these bombs, just to give you a kind of a more illustrative number. And more than half of this energy, of course, since the system is warming, is emitted again by long-wave radiation, but the rest is used to warm up the oceans. This is about 90% of the remaining energy. And the rest is used to melt ice, to warm up the continents, to accelerate the biochemical processes, to accelerate evaporation, and also to modify and accelerate the circulation patterns of our two fluids, which is the atmosphere and which are the oceans. And from this point onward, we can only work on scenarios, and we have 4 different emission scenarios, all based on socioeconomic scenarios, and they show us the emission rates, how they are going to proceed until 2100. And we see the business as usual is the red one, and we have 2 ambitious scenarios, socioeconomic scenarios, which is the yellow one, and the bright blue one. And we have one which has to be gone for if we would like to reach the second target, or the 2 degrees Celsius target of the Paris Agreement. And this one makes very much sense. It's a very ardent one, it's a very ambitious one, but this is the only one which really makes sense, and we will see that in the next slides. If we follow this dark blue scenario, then we can stop warming by 2100. Then we can keep a bit of the Arctic sea ice at the end of the summer of each summer season, which would be totally gone if we follow the red line. Arctic sea ice has a kind of a feedback effect, since the more we lose, the more we take up heat, and the more the Arctic warms. And we have to know that the Arctic has already warmed by about 4 degrees, not just 1.1 as the average. And we can also stop the ocean acidification, which is due to the uptake of carbon dioxide in the ocean water, and which lowers the pH value. But there is one variable which cannot be stopped, and this is the mean sea level rise, even if we keep on going on the blue scenario. And that has to do that mainly the melting of ice is still going on. It's like taking an ice cube from a fridge and you put it on your table, and that's not gone immediately. It takes some time. And there is also the continuous uptake of energy from the atmosphere and the continents into the ocean, which takes also much longer. And so there is the ocean heat content, which is going up, and the expansion of the ocean water due to that. There is the Greenland ice mass loss, there is the Antarctic ice sheet mass loss, and there is the glacier ice mass loss, all driving the rise of sea level rise higher and higher. And we are still have to deal with beyond 2,300 from what we have already done right now. If we now look at different systems, how they actually are put under risk and how they could potentially adapt to this risk, if we just compare it, or if we put that into the context of the rising sea level on the blue line and here on the red line, then we see megacities, for instance, they are coming under risk. They are already on the light risk. Here is the scale of different risks. They are coming under risk, and they are getting into risks even higher if we continue with the business as usual. But they have a kind of an adaptation potential, which is the second column for each system. The urban atoll islands, mainly in the tropical oceans, the Pacific Ocean, they are very much more under threat, and they can hardly do anything against. Large tropical agricultural deltas, they also are very much under threat, mostly because of salinification of the groundwater, and there is not very much you can do against, even with technologies. And the same is true for the Arctic communities. They can hardly do anything against being in danger, against being exposed to higher risks in both cases. If we now look what this 1.5 report of IPCC has told us about a series of different systems, just comparing the 1.0 degree, 1.5 degree, and 2.0 degree Celsius warmer world, and the effects on different systems, then we don't go through all those, but we see that some systems are already very much under pressure, as for instance the warm water corals, or the Arctic regions, or the coastal flooding, or coasts that are flooded, small scale, low latitude fisheries. And the scenarios would get worse and worse the more you go toward 2 degrees Celsius and beyond. So it's really, the key message is here that it's really worth to do something and try to keep the 1.5, and we need to keep the 2.0. I'll come back to that. Anyway, the big problem, just to put it into a big picture, is that since 1 million years we have experienced a glacial interglacial cycle where the sun, to put it short, told the system to warm up, and the temperature went up, the sea level rose through the processes we know, and then the sun gave the command, so to say, to cool down, and the sea level dropped again because of the lot of ice which was accumulated on the continents. Now, for the time being, we have kicked out our system already from this loop, from this glacial interglacial cycle, and we have reached a point somewhere in between A and B here. A, B, C, D are paleoclimatologic evidences of the relation between sea level and global surface temperature. So we know roughly about these situations, and we also know that somewhere in between 1.5 degrees above pre-industrial and 2 degrees Celsius above pre-industrial, we would kick out our system into something which now scientists have started to call more and more the hothouse Earth. There is a very last and very immediate chance to stabilize the Earth, to keep it within a warmer world than so far, but still not getting totally unstable. Now, what are the signs we have observed already 2 weeks ago? There was this World Disaster Report 2020 from the International Red Cross delivered, and they calculated more than 100 disasters during the first 6 months of 2020, which is the COVID pandemic period, as they call it. More than 50 million people have been affected, and more than 10 different disasters affected over 250,000 people. But then comes the interesting number: 99% of the people affected were impacted by extreme climate and weather-related disasters. So we are in the middle of climate change, and also in the middle of experiencing already the effects to a very strong amount. Now, there is something which is very, very alarming, and this is the so-called tipping points. We have already seen that the Arctic sea ice is being reduced every year, basically, and has already reached very extreme low levels at the end of the summer. And it also there is no old ice left. It's only 1 year old ice left. So all the older ice is already gone, basically. And this has an effect through this warming, as I mentioned already, on Greenland, on the Greenland ice sheet. The Greenland ice sheet has already reached a point where we experience first melting on the uppermost levels of elevations of the Greenland ice sheet, which is an indicator that it's starting to being lost within a long time from now, but it may start already to be lost. We have also higher temperatures, as for instance the last the first half of 2020, when from January to June the temperatures in northeast Siberia were throughout the entire time 8 degrees warmer than usual, and this has caused permafrost thawing and forest fires. All this has also this warming has also an effect on our mid-latitude weather, since the temperature gradient between the mid-latitudes and the high latitudes in the northern hemisphere are decreasing. That means we have a change in our patterns of the atmospheric circulation, and we have experienced already these droughts, these extreme droughts now for 2 summers in mid-Europe. We have experienced boreal forests. We see pests changing the forest and so on, and all that has already an impact on the Atlantic circulation, which we know since about 3 months that it's not only slowing down since the 1950s, but we have been able to reconstruct it back to 1900. There's a gradual slowdown of the Arctic circulation that then has an effect on the Amazon rainforest, with a lot of droughts we have experienced, not just the Bolsonaro-caused changes, but also the droughts. The coral reefs are very much under threat, and we have, through these ocean currents, which are getting warmer, we have already effects on the ice shelves of West Antarctic mainly, but also first signs also in the East Antarctic. Ice shelves that have started to break off, which then have as a cause an accelerated outflow of the ice flows from the continental ice sheet, and this is something which we have some fear that is getting unstable in a very near time, and we have to take in mind that we have 7 meters of ocean of sea level rise in West Antarctica. We have 7 meters in Greenland, and we have about 60 meters in East Antarctica. So we are on the edge of changing the whole thing, and there is high urge to get it somehow managed, which is very difficult. We have on this already known plot reached 2019, and in order to get down to this net zero, this reduction must be much more dramatic than suggested by the dark blue scenario. And we have to go through this intermediate step, else we have lost the battle. So this would be minus 45% compared to 2010, which is minus 55% compared to 2019. There is a more detailed plot showing this, and also including the greenhouse gases, which are not only from CO2, there is also methane, and there is also the N2O, and they have to go down very quickly along the green line in order to reach the 1.5 target, or the yellow line in order to have a chance to stay within the 2 degrees target. But these are the dark blue is the current policies. Even though we had this little reduction through the COVID period, but then the current policies, they show and sign steeply up again. And even this promised pledges and targets of the national governments, they go far beyond what we need to do. And I just leave you, instead of having a final slide, I just leave you with this distribution among over sectors of the global greenhouse gas emissions, and my presentation. Thank you very much.
Well, I would like to stimulate everyone who's following us right now, close to 700 people. You are able in the chat to ask questions. We will have all the presenters on stage again at the end of the last presentation. But I have received 1 or 2 questions already now, Georg, which I would like to ask. Someone is writing that he or she heard a couple of times that a statement from people working in this area that the moment the permafrost is starting to thaw, the game is over. Is this too pessimistic?
The point is that with the methane, we cannot so easily detect whether there is already considerable exhalation from permafrost. If that starts, then we are into big troubles. And there are indicators for kind of a start in different spots. We have only so far one reported measured increase in emission, that is from the Baikal area, but we are waiting to get data from northeast Siberia, where we had this exceptional warm period in the first half of 2020. So this would put us under deep trouble now.
Thank you very much. There's one question, certainly not easy to answer. So what is the first thing to do?
I don't think that there is a first thing. We have, if you look to this final plot, we have to start everywhere, and we have to radically change our systematic approach, or let's say we have to change our market system, our system of industry, of agriculture, of almost everything. We have really to go a very tough way. And the 1.5 report has shown how to do that, and has also shown that in a global perspective, the well-being of the people would increase if we would go that way. So there are much more synergies with the so-called SDGs, the Sustainable Development Goals of the UN, if we would follow the change in energy, in types of energy, going to renewable energies, in reducing the energy, and by changing the land surface, the use of land surface.
Thank you very much, Georg. I think this is enough for the moment. We'll have you back on stage again. And you brought up already the topic agriculture and how agriculture is involved in the issue of climate change and greenhouse gas emissions. And this brings us to the next topic and the next speaker, which is Frank Mittlöhner. He will talk about rethinking methane, livestock's path to climate neutrality. First of all, I have to say, if I'm right, he is in the middle of the night, Frank. So I'm very happy that you went out of bed or probably came straight back from the bar. However, I know it's very challenging to be up in the middle of the night. We appreciate this very much. You are in California. He is a professor and air quality specialist in cooperative extension in the Department of Animal Science at the University of California, Davis. He received his master's degree in animal science and agriculture engineering in Leipzig, and he is working since many years in the US. He is an expert for agricultural air quality, livestock housing and husbandry. Overall, he conducts research that is directly relevant to understand and mitigate of air or the mitigation of air emissions from livestock operations, as well as implications of these emissions for the health and safety of farm workers, farmers, and neighboring communities. He has served on different levels around the topic. He was involved in the report and project done by FAO. He has served as a workgroup member on the President's Council of Advisors on Science and Technology. He has published many papers. He gave a couple of 100 talks about this topic. We're very happy to have you here on board, Frank. The floor is yours.
Thank you very much. Let me get my screen going. Okay. Can you see my screen? Okay, I cannot hear you. Oh, you can hear me. Okay, excellent. Very good. Well, good morning, everybody. It's a great pleasure for me to be here today and to talk to you. And the title of my talk is Rethinking Methane. So first, I want to so you can still see my slide, yeah? Because everything is looks a little strange on my side here now. Can you still see my slides? How about now? Can you? Okay. 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 So first of all, I want to make one thing very clear, and that is that methane, of course, is a very significant climate pollutant, and none of what I'm about to say changes that. However, I think that the narrative around methane from livestock needs a nuanced discussion, and I will. I hope that I will convince you. First of all, if you want to follow up with what I'm about to say, I put a video on YouTube. It's called Rethinking Methane, and it's a 5-minute video, easy to share. So if you Google YouTube and Rethinking Methane, you will get there. So first of all, to those of you who don't regularly deal with greenhouse gases, what do they do? Why are we concerned about them? Well, they are heat trapping in general. That's a quick way of saying it. Imagine the sun radiating down solar beams to the surface of the Earth. Normally, without human activity, they would be reflected back into space. And but these greenhouse gases such as CO2, methane, nitrous oxide, and so forth, pretty much form in let's say a blanket of our atmosphere, keeping that heat from the sun closer to our Earth, and preventing the solar load of that solar heat from going back into space. And that's really important. Without these greenhouse gases, life on Earth would be too cold. So we are happy to have those greenhouse gases. The problem is we have too many of them. And human activity is accelerating that process, and hence we need to do something about it. as my colleague so excellently stated. So today's talk will really focus on methane, one of the greenhouse gases. When comparing the various greenhouse gases to one another, gases such as CO2, methane, nitrous oxide, then oftentimes a matrix is used called global warming potential, or GWP, and this term will pop up during my talk repeatedly. The global warming potential compares different greenhouse gases and its relative potency to one another, and it compares everything to CO2. So the global warming potential 100 refers to the ability of these gases over a period of 100 years to affect climate. And so it says that methane is 28 times more heat trapping than CO2. Nitrous oxide, 265 times more potent than CO2. Hence, the urgency to address methane. It assumes, this global warming potential 100 assumes that methane, 1 ton of methane, for example, is 28 times effective trapping heat as 28 tons of CO2. So let's say if you were to run a dairy or beef operation and you were to produce 10 tons of methane per year, all you need to do is multiply the 10 tons you produce times 28, and then you have 280 tons of CO2e, or CO2 equivalent units. It assumes that all you need to do is really multiply the amount of methane you produce by 28, and then you have the equivalent amount of CO2 calculated. And this is how oftentimes different activities, such as eating a kilo of beef versus driving in a car a certain distance or so, this is how these comparisons are established. As I said, I will focus on methane, and in contrast to CO2 and nitrous oxide, which are largely only produced, methane is not just produced, but methane is both produced and destroyed. And this slide shows where and how. You see on the left side various sources of methane, such as fossil fuel production and use, agriculture and waste, biomass burning, wetlands, and so on. All of these emission sources emit a total of approximately 560 teragrams of methane per year, and that's global. This is where, for many people, the discussion stops, but it shouldn't, because methane is not just emitted, meaning being put into the atmosphere, but if you look on the right side, you'll find that methane is also destroyed, and not at a small amount. You see that the total methane sinks amount to 550 teragrams. So 560 are emitted and 550 are destroyed and or pulled into the soil. So, and you see this large arrow there pointing downward, which says sink from chemical reactions in the atmosphere. This sink from chemical reactions refers to a process called oxidation, where if you have a methane molecule in the atmosphere, within a relative short period of time, it meets a radical, that's what it's called, a so-called hydroxyl radical in the air that steals the hydrogen from the methane and destroys it. And that happens in a relatively short period of time, as you will see in a minute. So globally, the net methane is not 560 teragrams, the net methane is depicted in this red box here. So it's the difference between what we put out versus what is being destroyed. So this number is still too high, and we seek to further reduce it, because you will see later that the reduction of methane has not just unique challenges, but also unique opportunities, even in the short term, associated with it. In addition to the global warming potential, an additional nuance around these greenhouse gases is the so-called lifespan of these gases. While CO2 and nitrous oxide are so-called long-lived climate pollutants, once they're in the atmosphere, they stay there for a long time. In the case of nitrous oxide, over 100 years. In the case of CO2, over 1,000 years. So again, they are long-lived climate pollutants that are not really destroyed. Methane is both produced and destroyed, almost at equal rates, as I showed on the previous slide. And this obviously really matters, because when something has a short lifetime and lifespan like methane does, then that offers us different avenues for mitigation. I now want to talk to you briefly about the so-called biological or biogenic carbon cycle. And it depicts methane, CH4, and where that carbon in the methane, in that CH4, where it originated and where it ends up eventually. So how or what does plants need to live? I'll just boil it down to the basics right now. What do plants need to live? First of all, during the process of photosynthesis, plants need sunlight, they need water, and they need carbon. And the carbon that these plants need, they take from the atmosphere in the form of CO2. That's nothing new, we all know that. They then produce oxygen and they produce carbohydrates. These carbohydrates could be in the form of cellulose or in the form of starch. Sooner or later, a bovine comes along and eats that plant material, whether that's grasses or whether it's corn, which of course also is a grass, or whether it's legumes or so. They eat that plant material, and a fraction of that carbon that used to be in the air before it went by photosynthesis into the plants, a portion of these carbohydrates are then converted into, for example, enteric methane, or into methane that's generated by the animal's manure. That methane contains, of course, carbon. And this carbon is not new carbon that we have added to the atmosphere for the first time, but this carbon contained in this methane is recycled carbon because it originated in the form of atmospheric CO2. It now takes about a decade for the carbon that's contained in that methane to undergo a process called hydroxyl oxidation. Hydroxyl oxidation. So in about 10 years, that methane is broken down again into CO2. And again, this carbon that our livestock puts out is not new additional carbon, it is recycled carbon. And that carbon is then converted back into CO2 and added to the atmospheric pool of CO2, from which plants take on carbon again during photosynthesis. So it really is a carbon cycle, a cyclical event of carbon moving from atmospheric CO2 to plant carbohydrates to methane belched out or stemming from animal manure, and then again going back to CO2. Why am I showing you this? I'm showing you this because the biogenic carbon cycle depicted here is really quite different from, let's say, the carbon in fossil methane or other greenhouse gases that stem from other human activities. If livestock herds remain constant and don't increase in numbers, if they were to remain constant like they do in most developed countries of the world, then that means the amount of methane produced by our livestock and the amount of methane destroyed through hydroxyl oxidation are roughly in balance. The problem occurs when methane goes up, like it currently does in developing countries, which have an increasing demand in animal source foods, and hence they're growing their herds. Their methane goes up, and that's a problem, and we don't want to see that. They actually could produce an increasing amount of animal source foods with constant or even shrinking herds if they were to increase efficiencies, like we have in most of the developed world. But if you manage to decrease methane, something really amazing happens. So remember, stable herds, stable sources of methane do not add additional warming to our climate. Decreasing methane has real opportunities associated with it, as I will show you in a minute. So contrast this biogenic methane to fossil carbon. Fossil carbon is oil, coal, and gas, or that's the origin of it. And oil, coal, and gas is nothing other than plant and animal material that died and decayed and fossilized hundreds of millions of years ago. It's actually all the biomass that was on Earth for a long, long time, for millions of years, that then was locked down in the ground. And over the last 70 years or so, pretty much since 1950 in a major way, we have taken that carbon out of the ground, this fossil carbon out of the ground, And after extracting it from the ground, we have burned it with cars, trucks, trains, planes, ships, and so on, putting that carbon that was down there into the atmosphere where it accumulates. And year after year after year, we see CO2 going only one way, and that's up, 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 and up. That is not a cyclical event in the short term. It is a one-way street from the bottom, from the ground up into the atmosphere. And in my opinion, this is the main culprit of human activities affecting our climate. So here a contrast between, on the left side, fossil fuels that, as I just said, were locked in the ground. That's ancient carbon. We are extracting it, we are burning it, we are putting it into the atmosphere. Versus the carbon cycle of livestock, where you have atmospheric CO2, just really quickly, going into plant during photosynthesis. A portion is stored above ground, and a larger portion even below ground. It's going into the roots, and from there into the soil, where it goes into a process called carbon sequestration. It's pretty much locked in the soil. And soils are an extremely important sink for carbon. So livestock then eats a portion of that above ground carbon and belches some of that carbon out in the form of methane, which is then after 10 years converted back into CO2. The same is true for the manure methane that stems from those animals. That's also reverted back into CO2. So as long as these livestock herds remain constant, the amount of carbon that's going through this livestock system is not increasing, it's staying stable. If we, however, decrease the amount of methane from livestock, then we are doing pretty much the same as what we do when we plant trees. When we plant trees, and many governments now incentivize that, then that means that these trees that are being planted are sucking carbon out of the air during photosynthesis. And that has a net cooling effect and an impact on pulling carbon out of the atmosphere. By reducing methane, we do something very similar, as you will see in a minute. So on this slide, really quickly, a one-way street on fossil greenhouse gases, and on the biogenic greenhouse gases, we have a cyclical event. So you should not compare cars versus cows. That is one of the no-nos that people do and often do, but it's very flawed. Now, a depiction of the differences between a long-lived greenhouse gas, such as CO2, versus a short-lived climate or greenhouse gas, such as methane. The next couple of slides here stem from Miles Allen, a professor from Oxford University, and his team, who brought into the discussion a focus on how methane is really different from CO2 and nitrous oxide, and why we shouldn't use GWP 100, that unit that we have been using for the longest time, to depict its impacts. So first, we look at CO2. Imagine you driving to work from home every day of the week. Monday is day 1, Tuesday is day 2, and so on. So you drive to work on Monday. You put CO2 into the atmosphere when you burn gas. On Tuesday, you drive again, and you add new additional CO2 to the atmosphere, which you add to the existing stock that you put in on Monday, which is, of course, still there. On Wednesday, you drive again, and you add additional new CO2 to what you added earlier this week. And not just earlier this week. Any time that you've ever driven a car, every time that you've ever burned fossil fuels through any activity of your life, or your parents' life, or your grandparents' life, all of that carbon is still there. The vast majority is still there. Some of it might have been taken up by oceans and vegetation and so on, but the vast majority is still there. And so this is why CO2 is referred to as a stock gas, because every time we emit new CO2, that is added to the existing stock of what we had put out before. That's why CO2 is such a problem, because every time we emit new CO2, we're adding to the existing stock. It's going up and up and up. It's cumulative. It accumulates in the atmosphere. This is in sharp contrast to the so-called flow gas methane. Flow gas does not accumulate in the atmosphere like CO2 does, because methane is both produced and destroyed almost at equal rates. So as long as your sources of methane stay stagnant, you're not adding new additional carbon to the atmosphere and hence not new additional warming. So if you, for example, have a dairy that you started 50 years ago, then only the first 10 years you added an additional pulse of methane to the atmosphere. After the first decade, due to the lifespan of that gas, you didn't add new additional methane to the atmosphere, but the methane you put out in the second decade replaced the methane you put out in the first decade. So that's the way flow gases work, and that is what methane is, a flow gas. The problem, however, is that this GWP 100 matrix that I showed before acts as if methane were a stock gas like CO2, as if it were to accumulate in the atmosphere, when indeed it's a flow gas that doesn't accumulate in the atmosphere. And why that matters will be made very clear on the next two slides, or the next following slides. Before I go there, just really briefly, there are a couple of blogs and so on that are relatively non-technical, written by Miles Allen and by Dave Frame and so on, several of the key authors of IPCC. But then there are also numerous peer-reviewed publications published in Nature and Science and so on, along the lines of why we really need to rethink methane. This topic is of absolute high importance to animal agriculture, in my opinion. And here's why. I will now lead you through three scenarios. The first scenario is one by which we increase methane by 35% over a period of 30 years. The second one is a scenario where methane over 30 years slightly reduces. And the third one is a scenario by which we reduce methane strongly by 35% over 30 years. Okay? So again, first scenario, strong increase of methane. Second scenario, pretty stable, slight decrease of methane. And the third one is a strong decrease by 35%. How would these three methane scenarios look like if depicted by this old matrix GWP 100? GWP 100 depicts these three scenarios in the following way. It says that if we increase methane by 35%, we have a strong increase in the so-called CO2 equivalent units. Strong increase. Nothing new here, and I agree. But when we hold methane pretty stable or even slightly reduce, GWP 100 still predicts a strong increase of CO2 equivalent gases, even with a stable or slightly reducing amount of methane over 30 years. But look what happens, what GWP 100 does when methane falls by 35%. Then GWP 100 still predicts a strong increase in CO2 equivalent impacts. And that is just not correct. These colleagues from Oxford suggested a different matrix called GWP star that actually looks at the impact of methane over time. And it looks at how methane actually warms the planet, how it contributes to a change in temperatures. Because GWP 100 doesn't do it. GWP 100 only predicts what a certain scenario change is of rising, stable, or decreasing amounts on CO2 equivalent units. GWP star, this new Oxford matrix, does much more. It predicts actual warming impacts over time. So if you look at GWP star, then the three scenarios are turning out to be the following. A rise of methane over 35% would mean a strong increase in warming equivalent units. And there's no doubt methane is a strong climate pollutant. We do not want to increase it. But look what happens, predicted by GWP star, when methane falls or is stable. Then we don't see any positive warming, and that means actual warming, occurring at all, because the amount of methane produced and the amount of methane destroyed are in balance with one another. And because there's a slight fall here of methane by 10%, you even see that the blue is south of the x-axis, and that means a little bit of negative warming. because we are decreasing methane slightly over time. But look what happens when you strongly decrease methane by 35%. GWP star predicts a strong impact on negative warming, and negative warming means that we actively pull carbon out of the atmosphere. We are now pulling carbon out of the atmosphere, leading to negative warming, and negative warming is nothing but a fancy word for cooling. In other words, a decrease of methane pulls carbon out of the atmosphere, much like planting trees, planting forests. But for some reason, policymakers have never really, and even scientists have never really understood that well, or at least have never discussed it as such. So here you see GWP 100 and GWP star compared and contrasted. You see that both of them predict almost the same when methane rises, right? They almost predict the same, but they predict something very different when we have stable methane scenarios or decreasing methane scenarios. In the case of decreasing methane scenarios, not just are the quantities different, even the sign is different from positive to negative. So vastly different prediction of the impacts of stable and decreasing methane impacts. And that's what we all after. You know, what Professor Kase just talked about, we want to predict impacts of activities on warming. And GWP star does that. It predicts impacts of activities on warming. GWP 100 doesn't do it. It simply predicts CO2 equivalent units. And it does so in an inaccurate way under stable and cooling conditions. Here, one more technical slide. It contrasts what happens when you either increase, hold stable, or decrease CO2 and methane, and what these impacts of increases, stable, or decreases are on warming. So you see, if you have a, let's say, power plant that increases the amount of power produced over time, then that leads to a logarithmic increase of the warming associated with that increase of CO2. If you increase methane, however, by growing your livestock herd, then that also increases warming associated with that increase in methane, but in a linear fashion. If you hold both CO2 and methane stable, then that means that the CO2 warming is still increasing because it's cumulative, while constant methane sources hold the warming associated with that methane stable. But look what happens when you decrease both CO2 and methane. When you decrease CO2, the warming still goes up until the point of net zero. At that point, you plateau with the associated warming. But when you decrease methane, you have an instantaneous cooling effect. People ask me, is methane a super pollutant? Well, it could be, but in my opinion, it's more of a super opportunity. So here at UC Davis, we do a lot of research on livestock emissions and how to reduce them through enteric emission reductions, feeding feed additives, or doing things with manure. And we help our state in achieving reduction goals. One of them is a methane reduction goal to reduce methane by 40% by the year 2030. Our farmers at first thought this is impossible, until the state partnered with our dairy, for example, sector in putting in, let's say, anaerobic digesters. You see here one. But in contrast to those that you see, let's say, in Germany, those covered lagoons here trap the biogas, 50% of which is methane, and convert it into vehicle fuel, into renewable natural gas. And that is highly incentivized by the state with strong credits. And so many farmers have already done technology implementations like that, that we now have reduced our methane by 2 million metric tons per year here in California, which equates to a 25% reduction of methane that we have already achieved in just 4 years. 25% reduction of methane from the California dairy sector, which by far is the most important one in the United States. So we can do it. I know others can do it. And I think even worldwide we can do it. Reduce methane and unleash its power to actually help us with the climate. I think that we are, if we do it right, on a path to climate neutrality, because if we manage to reduce methane, then that has negative warming impacts, which is a good thing, counteracting those impacts of nitrous oxide and others. There is, I believe, a chance for us reaching climate neutrality in animal agriculture in the decade to come, if we do it right. And policy has to accompany that. But the first step for that is to proper assigning the impact of methane, of short-lived climate pollutants, by using the right units. So with that, I thank you very much for your attention indeed. Just really quickly, if you want to look up some of the stuff that we do here at UC Davis, go to my center, the clearcenter.ucdavis.edu, and you find a lot of material there. So with that, I know we'll have some time later. Thank you very much for your attention, and looking forward to further discussion.
That was a very interesting talk and stimulating talk. I received a couple of questions, which I probably will keep for later. One is, of course, also dedicated to Gerd. What do you think about this type of measurements? So what will be the future in measuring methane, Frank? Can you give us an outlook, a short?
What will be the future of measuring methane is one thing, but quantifying methane, I think, is the more important one. Quantifying methane will have to be done, in my opinion, separately from the quantification of long-lived climate pollutants, because methane behaves differently in the atmosphere. It warms our planet differently. It has opportunities for cooling, and therefore we really have to use a unit that predicts the impacts methane has on temperature and not just on CO2 equivalents. And with that, I think we have unique opportunities, particularly in animal agriculture, by reducing that gas and having real impacts on climate. So in my opinion, in 5 years, we will look at the impact of animal agriculture on methane, on climate differently compared to the way we do it today. Today, cows are climate killers. In the future, I think there will be opportunities seen when it comes to reducing methane from animal agriculture, and that can have far-reaching consequences on overall warming.
Thank you very much, Frank, for this statement. I have a couple of questions for later. We will keep them and move on to our next author, to the next presenter, which is Umberto. He's already waiting. I received a couple of comments that the slides have been quite small. I had a similar problem. I thought it's just my glasses, which are not strong enough, but maybe on Umberto we have to ensure that the slides are really have the right size. So you will do your best, Umberto. Before you start, I just want to shortly introduce you. Umberto Bernabucci is a full professor in environmental physiology and ruminant nutrition at the Department of Agriculture and Forest Science at the University of Tuscia, Viterbo in Italy. He is a very well-known expert in the impact of heat stress on animals and livestock. I just want to remind you there was a very nice edition brought out last year, Animal Frontiers. He was a guest editor, and it's all about climate change and the impact of animals. Umberto received a degree in animal science. He is active since 25 years. We're all getting older, Umberto, in the areas of feeding and management transition dairy cows, feeding and management heat stress dairy cows. So his current research and the research of the last 20 years, I can also focus very much on the effects of heat stress and physiology, health, performance of dairy cattle, and the effects of nutrition and environmental factors, mainly heat stress, climate, on milk yield and composition. Umberto, we are looking very much forward to hear your talk. Take your time so that we have the right size of the slides. Please, the floor is yours.
Okay, thank you, Matthias. And so I try to share my presentation. So, okay, thank you very much. On to everybody. So, in the talk, I briefly summarized on climate change, and we will concentrate briefly on some aspect related to the impact of heat stress on production and health, and also discuss some aspects related to stress on livestock production systems. So, as shown before, data on annual global air temperature anomaly clearly show the temperature started to significantly increase since the beginning of 10 and it increased in the last 20 years, continue to increase. And important thing is really the of the increase. So our main dominance in particular, we have to count a specific thermal index, one of the most used PHI. PHI combines the effect of temperature and relative humidity. As you know, the typical chart showing the possible correlation between temperature and humidity.
Umberto,
yes.
Sorry for interrupting, but we have a very bad signal from your side. So either you have two mics open and we have this echo, but it would be a shame not to hear you. So I would suggest to start again.
So now it's better?
Yes, it's better. Thanks.
Okay. So, okay. This is a typical chart, but probably most of you know this chart. Just to show you our result of our studies. So in our study, we use the THI for characterizing the Mediterranean areas. In this study, we analyzed it, and the analysis demonstrated a high degree of heterogeneity of THI patterns over the Mediterranean basin, a strong north-south gradient, and an overall warming during the study period, which was particularly marked during the summer season. Results indicated that several areas of the basin present summer THI values which were unfavorable to animal welfare and productivity, and that risk of heat stress for farm animals is generally greater in countries in the south coast of the basin. In our second study, we described the THI dynamics over the Mediterranean basin in the period from 1971 to 2050 to evaluate possible future scenario, having in mind to provide useful information for farmers. So in this slide, I reported the summer period. The months was June, July, August. The figures represent the reference period, the Clino, and the evolution of the THI value from 2011 to 2015. As you can see, there is a significant tendency in gradual increase of THI from 2011 to 2015 in the Mediterranean area, and in particular, the analysis indicated that Spain, southern France, and Italy, THI will increase up to 3-4 units. So the Mediterranean area will be one of the hotspots of the world in the next future. So we also try to characterize the Grana Padano cheese production area in North Italy. So, and we were able to found an increase in the risk of heat stress in the future, also in this area. In summary, so the increase in temperature and THI, increasing the frequency of heat waves and alteration of rainfall frequency and intensity is expected in the future. And the increasing is not just for country occupying tropical zone, but also for nation in temperate zone. So just to highlight some impacts of our condition on health and production, mainly in dairy ruminants, and I will present our results. So briefly, the acclimation imposes biological responses to ruminants. The behavioral, physiological, and metabolic adjustment to reduce the strain and enhance the likelihood of surviving the stress frequently reduces animal performances and may compromise health or jeopardize animal welfare. So therefore, acclimation responses can lead to an altered welfare, and in situations characterized by extreme stress, the animal may succumb to heat-related complication and die. So the type and the level of these responses depend on several factors, including species, breed, type, and level of production. So just talking about reproduction, so hot season and seasonal heat stress negatively affect metabolism and then ovarian activity. So those negative effects lead to the alteration of reproduction efficiency, and the clinical consequences are this one: failure of artificial insemination, poor estrus, reduction of conception rate and pregnancy rate, and so on. As well known, heat stress negatively affects milk yield. In our study carried out on Italian Holstein population, we confirmed the negative relationship between THI and milk production, milk yield. But as you can see, the three parities had different THI breakpoints, showing different sensitivity to heat stress. In our recent study, the study I presented before, we combined the increase of THI and the losses to the increase of THI. We were able to construct the milk losses prevision chart. It was possible to highlight the areas at greater risk in milk production losses in terms of yield, milk protein, and milk fat in a very small area in North Italy. So about milk quality, I just very briefly show you the changes of fat and proteins. This is our study in which we found a decrease of fat during summer and decrease in proteins, but another particular changes due to the somatic cells count that increases always during summer period, and the greater value were during the 2003. The 2003 was very hot here, if you remember. So because of changes reported about milk quality, cheese-making properties of milk are strongly altered. So we observed an increase in rennet coagulation time, an increase in time and curd firming rate, and then a decrease of curd firmness during the hot season. As a consequence of the alteration of milk cheese making properties, usually cheese yield and also cheese quality is strongly reduced and altered during hot season in Italy. Just some data on health. So about immune response, we did an ex vivo experiment evaluating lymphocyte proliferation in dairy cows. And in peripartum dairy cows under severe heat stress conditions, lymphocyte functions are usually strongly altered. In other words, heat stressed animals become more sensitive to infections. So in this slide, in fact, in our recent study, we observe greater mammary infection incidence during summer and strongly related to the increase in THI level. So heat stress also significantly affects mortality in Holstein cows. Similar results are reported for other ruminant species and also in non-ruminant species. So in our retrospective study carried out for years 2001-2006, we found an increase in mortality rate in dairy cows, and during summer season we observed an increase in mortality rate from 14% to 60%. And mortality was strongly related with increased THI, and there was a strong relationship between THI and mortality in dairy cows, and the study was carried out in North Italy. So up till now, we have mainly seen how farm animals react when are exposed to hot environment. We will now try to analyze the livestock systems to evaluate what may happen under the effects of climate change and how sustainability will be affected. So first of all, very briefly, definition of livestock. Livestock is defined as domesticated animals raised in agricultural production system with the aim of producing food, fiber, and labor. So many factors influence livestock production systems, and this figure report all factors, but one today we will talk about just a climate effect. And considering the climate change effect, the impact of climate change on livestock can be direct and indirect, but the impact is mediated by several other factors like geographical region, animal characteristics, management, and so on. And the impact can affect the animal conditions, and then social, and then this can have a big social impact. So this slide presents schematically the classification of livestock production systems, considering two main criteria: the agroclimatic component and type component. So the first category includes the grazing pastoral systems. These systems utilize more than 3 billion hectares of arid pasture, where agriculture usually is not possible. And ruminants represent almost all the reared animals in those systems. Pastoral systems today provide about 24% of the total world cattle meat and more than 30% of small ruminant meat. The second include the mixed agrozootechnical systems. These systems use about 2.5 billion hectares. According to Steinfeld, we can subdivide this system in two categories: the rain-fed mixed systems and irrigated mixed systems. All the main species of animals are reared in mixed systems, and globally we can estimate that today these livestock systems provide the largest amount of world meat and milk production. And the calculation made on FAO data give a production in all mixed system about 9% of world milk and more than 46% of total world meat. All these mixed livestock systems have a common characteristic of producing crops to supply feed for animals, totally or partially. The third category is the industrialized and land-based livestock systems. The industrialized systems are the most important systems used to produce pork, usually, and poultry. These systems provide world consumers about 71% of poultry and 55% of pork, and in some zones, like, for example, in Europe or in Italy, also beef. Globally, industrialized systems provide 45% of total world meat. And the third category is the combination of the agrozootechnical and industrialized systems. So now, regarding a possible analysis we can do, we have two main questions to answer. The first one is which production system will be more affected by climate change? And the second one is which modification will there be in the livestock system under the effect of climate change, and what can we do to cope with these effects while maintaining at the same time the sustainability? So to answer the first question, we can divide the livestock system in three main levels regarding climate dependence. Considering the dependence and vulnerability, we have the systems totally dependent by climate, systems partially dependent by climate, mixed, rain-fed and irrigated, and system independent or slightly dependent by climate. So dependence on climate establishes how much the animal performance, health, welfare, and nutrition and production are affected by the climate conditions in a short to medium period in each system. So these systems which are totally dependent by climate are the pastoral systems, where the animals are free or forced to graze and don't have any protection for direct climatic effects. Animals can avoid solar radiation also by taking shelter in shade or trees where and if there are any. On the contrary, the independent or slightly dependent livestock systems are those systems which rear animals in barns, where temperature, humidity, solar radiation, wind, and so on are totally or at very high level under structural and managerial control. And industrialized and landless systems belong to this group, and also almost all mixed agro-zootechnical systems belong to this last group. We must point out, however, that farms belonging to mixed systems can have highly variability in climate dependence due to their location worldwide and whether they are rain-fed or irrigated. So, answer to the second question on modification of systems. So I reported some schemes in which I indicated changes possible for species feeding and production in all systems. So the pastoral system will be exposed the most to climate change. And in any case, the pastoral systems has no or very little possibility to cope with the negative effect of climate, neither on animals nor on pasture. And poor nutrition and heat stress increase the risk of poor health in animals. And we have to expect a reduction of stock and production in these systems, especially in zones negatively affected by climate. Sustainability of the soil could decrease due to overgrazing and worsening of the soil, further exposed to desertification. Finally, some small local animal population well adapted to pre-existing environment could disappear, thus compromising also animal biodiversity. And although these systems provide less than 10% of the total world meat and 12% of the total world milk, they are of high social and economical importance for local inhabitants and of very relevant interest for our culture. About mixed rain-fed systems, the possibility to cope with the effects of climate change in mixed systems will vary according to the area and the available technologies and extension service where the systems are located. The adaptation of barns could represent a fundamental element in limiting the heat stress for animals, especially in occurrence of heat waves, both in rain-fed and irrigated systems. These systems have to pay attention in producing crops and animals less sensitive to heat stress, and in particular, they must be conservative in water. we can expect a modification of the animal species and breeds raised in these systems. And we can forecast that either beef or milk could be seriously damaged by global warming, especially in mixed ram-fed systems. Probably also pork and poultry production and eggs could be strongly affected depending on the characteristics of housing and on the economical possibility to adapt the barn microclimate and to the availability of grain from the market. Mixed irrigated systems, in these systems, all modifications are possible if there will be the possibility to irrigate and to adapt the barn, for example, providing efficient cooling systems. About industrialized systems, the new climate scenarios may induce negative effect even on industrialized livestock systems because they are completely dependent by the market to feed the animals. Moreover, soon the availability of some grains for animal feeding could decrease due to the increasing demand for human consumption and to the perspective of producing biofuels. However, increased capital investment will be needed for ventilation and cooling system and for the thermal isolation of buildings to cope with increasing temperature and heat waves frequency. The difficulties in increasing animal production in the other systems will favor probably the development of intensive specialized systems to produce more pork and poultry and to a certain extent cow milk and beef. Probably the absolute reduction of gas emission per unit of product could represent an important environmental advantage in industrialized systems. But in any case, the concentration of animals on a small surface will determine problems because of the huge amount of manure which must be disposed of. So just to summarize, for extensive and intensive livestock, how the systems have to adapt or change under climate change scenarios, we say that probably this system will decrease in the total in the future, both in developing and developed countries. Paddocks will have to be redesigned to improve the shaded areas and also improve the availability of water. Farming units will increase in size with less animal per area unit, and conservative stocking rates, pasture conservation, and rainwater harvesting should be improved. Indigenous adapted breeds will dominate but should not be to the detriment of production level. Production efficiency, of course, will become a paramount. Marker assisted selection will become more relevant for genetic improvement, and diversification of species will be needed. Probably more stock species will begin to dominate, and the production cost will increase to some extent. Also, in extensive systems, a relatively high skill set level will be required for extensive livestock farmers. Considering the intensive systems, as I told you before, probably there will be an increase in intensive livestock production systems in the future. Monogastric species will be seen as more environmental friendly compared to ruminants. Intensive livestock production will move closer to the urban areas, and housing systems will change, in particular, for example, to increase the self-sufficient energy supply, air filtration, recycling of water, and sophisticated cooling systems. Ruminant and monogastric diets will become more refined, keep in mind the life cycle environmental production cost. Drought-tolerant grains will form part of ruminant and monogastric diets, and manure management of intensive systems will become industrial processes in order to minimize environmental impact and to generate reusable energy. Genetic selection will be leaning toward more efficient subjects under intensive conditions. Market-assisted selection will become essential. And there will be a shift from extensive to intensive production systems in developing countries. A very high skill set level will be required for intensive livestock farmers in order to deal with the adaptation mitigation aspect of climate change. So coming to the conclusion, first of all, I would say that the challenge of climate change is unprecedented for humanity and requires a significant change in our way of thinking and acting. We know how future climate change scenarios will affect agrosystems, landscapes, agricultural yields, and local and global economies. But how these changes will affect the society in general are still not known. The bottom line is to have all the relevant data available to make informed decisions. All relevant information should be used by animal scientists, veterinarians, climatologists, and farmers, together with trend observed in practice to adjust a specific production system as the situation develops. Institutions also play a substantial role within this transformation process. And in conclusion, there is a need for additional public-private partnerships to deal with complex issues, such as those related to human health and water governance, to support non-litigious mediation of environmental conflicts. So thank you very much for your attention.
Thank you very much, Umberto. I think stop sharing the slide, and you may mute the microphone for the moment. I think everyone is on screen. Hopefully, yes, because we will start the overall discussion directly, including you, of course, Umberto. Thank you very much. I had tried to follow the chat and all the questions. Unfortunately, I'm a man. It's quite difficult to follow your interesting talks and at the same time to write down the questions. So maybe I miss one or two. But there have been many comments and missions and questions. First of all, congratulations to all of you. The people have been really happy with your talks. Very satisfied, beside the president, they say. So let's start. Start with you, maybe, Georg. I guess this is dedicated to you. It is related to the talk of Frank, and the question is, how does IPCC look at this theory of rethinking methane? Any comments from your side? Do you agree? Disagree? What do you think about?
First is that let me put it that way. 5 years ago, I think hardly anyone had still the feeling that we can do it with the 2 degrees Celsius. The windows were closed, so to say. And then was this 1.5 degree special report, which was forced by the Paris Agreement signatories, and which then came out in 2018. And not to little surprise to some of us, it reopened a window. And when I was not part of that writing team, and when I asked, when asking for what was the reason that you can reopen, then they put as one of the main answers or main reasons that they have now been able, under this pressure they had, but they had now been able to fill in, to add in to the big models, the global models, the Earth system models, they call it right now, a more sophisticated carbon cycle tools, including also these sub cycles of the methane that Frank has so nicely explained. This is one point. So people are aware of that, particularly the modelers, and it is already to some extent implemented, not maybe to the extent that Frank would put it, because people are still working on it. The other point is that Frank was only talking about the, so to say, day-to-day production of methane and then destruction of methane. Our big concern is not that one. The big concern is the exhalation of almost fossil permafrost methane, and there is nobody there to destroy that. We cannot have so many animals on Earth. That is the big problem. Yeah, and then I had a question to Frank. What would be the ideal balance? Because you said if we keep the present day stock and keep that in balance, so to say, or then making a balance out of the methane, then we would do a good job. But hadn't been a balance with the stock numbers of, let's say, 1900, the ideal ones. So aren't we by far too much into an imbalance due to too many animals on Earth?
Yeah, so I think this is a really critical question. And so obviously people have nutritional needs and they include animal source foods. And so the question is, how do we satisfy, on the one hand, the need to have animal source foods, and on the other hand, the environmental impact. So I believe that, and we have shown this in many developed countries, that we can satisfy the nutritional demands of animal source foods while at the same time strongly reducing short-lived climate pollutants such as methane. I think that we can achieve 30–40% reduction of methane without changing any numbers in 5 years, in 10 years. I have done research here, for example, in reducing enteric methane, where we achieved anywhere between 10 to 50% of methane from these animals without changing any numbers of animals. So we have to have a balancing act of giving people what they want to eat on the one hand, particularly in developing countries where people are nutrient deficient, while at the same time not increasing environmental harm. And that's what I'm trying to do.
Mm-hmm, mm-hmm. But one had to add also the immediate CO2 emissions from transport, from managing, from whatever, from the cow to the plate, so to say, to the table.
Yes, but when it comes to livestock, by far the greatest contribution is through the animals themselves. And that's enteric emissions, for example, belched out, as well as animal manure. That by far is 80% or so, or more, of their carbon impact. Transportation of goods and refrigeration and so on, that's minuscule compared to the direct emissions via manure and enteric.
Okay, thank you.
Thank you both. Frank, I'd like to follow up on this topic. There was a question related to intensive, extensive versus extensive system. What is the better one? And the question is, isn't the use of crops for ruminants more the problem than the direct methane emission? So what is better, the intensive, extensive? Are there any arguments pro and con?
There are arguments pro and con, yes. And it's a hotly debated topic. There are some people who say we should only have extensive and no intensive, and there are others who say intensive are much more efficient. Both of them are right. And that sounds really strange, but intensive systems can finish an animal way faster. For example, a corn-finished steer in the United States lives half the life span of a grass-finished steer. So you could argue there's much less enteric emissions, much less manure produced, less feed consumed, and so on in the intensively raised animal. But on the other hand, the extensively raised animal is on grassland. That grassland manages to sequester quite some carbon. We find large amounts of carbon going into the ground in grassland systems. And we oftentimes have not really accounted for that appropriately yet. So I do not want to pitch the one system versus the other system, but I think there's room for both. Now, feed itself is a significant component. The feed that livestock consumes makes up 40%, that's 40, of the carbon footprint of livestock production. So the feed, yes, is a significant component, and here in particular the nitrogen applied as fertilizer, which then can become nitrous oxide.
Thank you very much, Frank. There was another question, but a comment as a recommendation has to be seen. And it says simply go vegan and you solve the problems. Is this true, Georg? Will this really make a significant difference if we all go vegan?
I think, apart from the fact that this is not realistic and it would be very, very difficult, I keep myself back from giving such suggestions for the reason that I think vegan is not vegan and meat is not meat. If you go into, and Umberto may disagree with that, if you go into the huge industrialized agriculture, then this causes, through the nutrition, through the use of energy, a lot of impacts, negative impacts to the climate. Not that much as we have heard through the methane cycle, but through the other things. If, for instance, I'm living here in a small mountain village and people around have livestock and they hunt, and I would be excluded from this community if we would not eat meat from time to time. I'm, so to say, a 75% vegetarian, not a vegan. I think this is not the solution, but on a global scale, if we would reduce the consumption of meat, we could contribute, I'm pretty sure. And not because of the methane, it's because of the nitrogen and because of the additional use of energy, which is mainly fossil so far, and hopefully will change into renewable energy.
Thank you very much, Georg. There's a question, probably Umberto, for you, is the question, is there potential in using agroforestry livestock systems? Is this the future probably, and what are the advantages of such systems?
Okay, yes, I did not present the data on agroforestry and silvopastoral systems because of the time, but yes, it's a good system because there are many data available that demonstrate that the intensification of of the agropastoral system using, where possible, the silvopastoral systems improve the meat production, meat production, but also save soils and have positive effect also on methane and CO2 emissions. Sure, but where and when is possible? Of course, it's not possible in all parts of the world, but in South America, for example, there are many nice examples of silvopastoral systems. So if you would like, I will show you the slide, but you know, it's the same because I have.
May I stay with you while you have the mic open? There was a question dedicated to one of your presentations, to one of your slides, where you have shown a higher mortality rate related to heat stress, to increase on temperature. And the question was simply if this higher mortality not simply reflects the action of the farmer, that he's culling animals because he has a reduction in feed production.
No, we did a big experiment in North Italy, and we found also a strong relationship between THI and mortality. When THI is up to 80, the maximum THI, the mortality starts to increase. It's not due just to the reduction of feed intake. It's not so simple, but there are many factors that we observed in strong relationship between THI and heat stress and mortality.
I may stay a second with heat stress. There is the question, most of the times in these type of studies, the THI is used as a parameter to measure heat stress. Is this a good parameter? Are there any better around? I mean, a couple of things are not taken into account if you base stress on THI.
So why we use usually THI? So THI, yeah, it's easier to measure, and but there are other indexes or indices, of course. So we used another index in collaboration with our friend from Australia, for example, and we published a recent paper using a more complicated index, and we found a nice results. For example, comparing those two index. Of course, THI is easy to get, because just if you have temperature and humidity, you can calculate THI. But in our condition, for example, when we use in the barn and for ruminants, THI is a good index, but in another situation is not so good.
So if you go to the possibility of using the variation in genetics, based on genetics, in how animals reacting to heat stress, so what would be the ideal parameter to select for? Is this the reaction of an increasing THA to the yield, or what would be the right parameter?
So we work with dairy cattle, of course. I don't have experience on monogastrics. So we use a THI, and we use the data available from Breeders Association. Like this approach was used also in the past by I don't remember the name, Ignazio. I remember the name, but not the surname. Mitzal, sorry. And so probably we have to try to understand which parameters easy to measure, cost effective, is useful, and is associated with other aspects of other parameters that are more linked with heat stress conditions. For example, I don't know, rectal temperature is one of these, because today using the livestock precision farming and sensors probably will be in the future easier to measure body temperature. Some data report also the rumination time, for example. This can be associated, or milk production, if we talk, if we consider dairy ruminants, of course, milk yield and milk quality. So are data available, and then we can use it. So we had some results in which we demonstrated that including THI in a typical model it's possible to separate, to discriminate the more or less sensitive bulls.
Thank you, Umberto. Sorry, I'm jumping a bit between the questions, and there's a question for you, Georg. It is interesting to see, of course, that COVID has changed the life quite a lot. And the question is if this will have an impact on climate. Do you expect any significant positive impact from this COVID crisis? No travel, less consumption, whatever, or is this insignificant?
There was a major decrease on a couple of days in April 2020 compared to 2019, the same time period. It was just a couple of days. And then it was a global decrease in CO2 emissions of 17%. And the authors then, they extrapolated this into two scenarios, and that was early summer. The first scenario was when the first lockdown, and first wave and lockdown, was to be ended in July, and that would have made up an annual decrease of 4% of CO2 emission. And if this lockdown had lasted until end of December, so into next month without any interruption, then it had decreased the emission by 7%. So the effect was there, the effect is probably to be seen, but the point is whether we, and there is also the big danger and big risk, if we now make a fossil lock-in, which most of people hope, so they dare for, and they are just waiting for locking in immediately the whole system again. And if that is going to be fossil, be done fossil, so to say, then we not to jump back and beyond what we had in 2019, but we have also burned a lot of money. There will be no money for at least for the next 5 to 10 years left in order to change the system, in order to change or get money into the renewables, the reduction of energy, and. So there is kind of a signal here, but there is also a huge danger that it may have even a negative impact.
Thank you, Georg. Here's a question for you, Frank, directly speaking of California. The author says, what do you make of the argument that GWP is unfair to developing countries because it takes a country's historic emissions level as starting point for decreasing the rate of methane emissions?
Yeah, so that's a very important question around GWP star, the question of fairness, because the issue is that we are dealing with a grandfathering in of emissions across different sectors, and that is often viewed as unfair because a new source, let's say if somebody were to establish a new farm, then that somebody would go from 0 to a certain amount of methane, for example, produced, and that would be a net new contributor causing new additional warming, versus somebody who established a farm 50 years ago, 100 years ago. That is considered unfair by some, and policymakers have to sort that out. It's not for scientists like myself to sort out, but it is a topic that's discussed within the IPCC and others. There is the issue of developing countries and people in developed countries trying to keep developing countries from making the same mistakes. Yet oftentimes that's then perceived as neo-colonialism, and we have to be mindful of that. So we can't really criticize others for mistakes that we have made ourselves, but maybe in a partnership-like environment, really reach out and say, listen, instead of doing XYZ activities, let's work together on finding more sensible solutions for you, whether it's on energy, whether it's on food production, and so on. I think we need to get there. It's a convoluted and complicated question, it really is, but one that can and must be addressed.
Just add that those things were dealt with within the 1.5 degrees special report of IPCC. There is exactly those topics and those problems are addressed, and it's easy to find. It's ipcc.ch, and there you go for the SR 1.5 and look for the summary for policymakers, and you find then in the fifth section these equality issues and the benefits on a global scale, the well-being for the societies, which is put into relation with the targets of the CO2 or whatever this climate change target, the Paris targets. So it is dealt with. Yeah. Okay.
Thank you very much.
Can I ask a quick question, Matthias? Because we have Georg here, and I'm very curious about this question. So I hear that when it comes to, let's say, agricultural emissions, let's say New Zealand, for example, produces a lot of agricultural goods. And the place where these goods are produced in New Zealand is where the emissions are associated with. Okay, so the New Zealanders get the blame, so to say, for producing agricultural goods. Let's say Saudi Arabia drills for oil and they produce the oil and they sell it throughout the world, but they don't get blamed for that, but the places that burn that fossil fuel that they produce in Saudi Arabia. So how can it be fair, agricultural countries ask, that they get the blame producing food that they then export in other parts of the world when, let's say, a fossil fuel producing country like Saudi Arabia does not?
I'm not totally into that, but there are different views of looking to that, and I just know it from cloth production, and for instance, China is usually blamed for having a lot of CO2 emissions because of producing so much consumables, let's say, and there are analyses which show where they are consumed. And then a lot of that load goes on the shoulders of the Europeans, for instance. And if you just look down your body, I'm rather sure that you have something which was made in China. And that is somehow an analogy to that what you asked for. I do not know about detailed comparisons of New Zealand, Saudi Arabia thing, but on a general scale, this is well known and well analyzed as far as possible. Sometimes it's difficult to get back to the sources because made in China doesn't mean, or Swiss made these days does not mean that it's made in Switzerland. It's just 10% or something like that. So it's not that easy, but people are aware of it.
Okay.
And it's also interesting to hear that I had the opportunity twice to be in the final discussion when the summary for policymaker of a report has to be, so to say, approved word by word and line by line by the government experts. And then listening to what the Saudi Arabians claim for and the Brazilians claim for and others are fighting for, and how they diplomatically deal with this is an amazing experience. So it goes over officially 4 days, but that is then 4 days plus 2 nights. And usually it extends even into the next day. So it's a day and night negotiations, and they know exactly what these different things mean. Yeah, where it comes from, very quickly. They just argue like on a you can imagine.
Thank you very much, Georg. I guess Grete would say that we're living in one world, so it doesn't care if she doesn't care if it's produced in China, wherever. It's its emission, and this is what counts on the world level, of course. Georg, no, I want to ask you, Frank, as we have you still on board, and we're talking about different views. So can you shortly summarize if this is possible, what the view of Americans is on climate change and how to act? I guess it's a difference between California and other parts of the States. But what we hear over the last years are mainly coming from this still acting president, which gives probably not the right picture of what is going on in the US.
So I think that we have experienced a period that was kind of unusual. If you think of the time before the current administration, the Obama administration was quite active with respect to climate, and the next one will be as well. You will see that the United States will be very active in the climate scenario and will rejoin Paris. I have no question about that. Our current, so the Trump administration, was of course a huge exception to that, and of great concern to us. And there were states, many of them, that did not partake in that, that said, yes, we are of course part of the United States, but we are not getting out of the climate agreements. We are not loosening up our goals. Here in California, for example, we have very strict laws on reducing climate impacts, methane, other short-lived climate pollutants, long-lived climate pollutants, vehicle standards, emission standards, and so on. And in my opinion, a lot of those will be adopted nationwide very soon. California is oftentimes the first adopter in the United States, and oftentimes the role model, and I think it will be that way coming up in the next few months and years.
Thank you very much. Let's hope that you will have a new president. It seems still to be kind of unclear, but we're still optimistic that the change is coming.
Sure, yeah, that's for sure.
Thanks, Frank. We trust in you. So we're running out of time. It's almost 12:30, which is the time to end the plenary session. Two things I want to say is, first, the sessions are starting 1:45 and sharp in time, so be in the sessions. The second, I want to thank you for being here in the plenary session, for giving really very stimulating, interesting talks. Georg Gasser, thanks a lot for being on board. This is not the normal audience you're talking to. Umberto, thank you very much for being here. And Frank, I see it's really tough for you to still stay up. I guess you're going straight to bed. Thanks for staying up with us so long. Thanks to watching, almost 700 people who joined this plenary session. They excuse us for these technical problems we had. We are learning and we're getting better. So see you in session. Have a nice meeting. Thanks to you again. And I say bye-bye to all of you. Ciao, ciao.
Thank you. Bye.